Richard Feynman, one of the greats, famously called the only mystery of quantum mechanics.
Ah, yes. The double-slit experiment.
Exactly. He said it was impossible to explain in any classical way, and which has in it the heart of quantum mechanics. I mean, that's a pretty bold claim.
It really is. And it's why we're tackling it. We're looking at the double-slit, the quantum measurement paradox that arises from it, and ultimately what it all means for our understanding of reality itself. It gets weird fast.
It really does. And as always, this deep dive is tailored for you, using your sources primarily, the quantum measurement paradox and wave dissipation hypothesis. So our mission today is basically threefold.
Right.
First, we'll unpack the standard accepted scientific picture of how this all works, or at least how we describe it working.
The established physics, yeah.
Then we're going to look closely at an idea that sounds quite intuitive, this wave dissipation thing, but we'll see why it, well, ultimately doesn't hold up.
It's tempting, that idea, but yeah, it runs into problems, big ones.
And finally, that leaves us facing the really deep, still unanswered questions right at the edge of physics. So think of this as your shortcut to getting up to speed on one of science's biggest puzzles.
Absolutely. And the core puzzle, the paradox, is, well, it sounds simple enough. How can tiny things like electrons or photons act like spread out waves when you're not looking?
Creating those interference patterns.
Exactly. But then, the instant you do look or measure them, poof, they snap into being a definite particle at a single point.
Right. And what does that imply about our reality, the one we, live in?
That's the million-dollar question, isn't it?
Okay, let's dig in. Section 1, the canonical double-slit experiment, the foundation. We think quantum, we think 20th century, but this setup, it goes back further.
Oh, way further. Surprisingly far, actually. Back to 1801, Thomas Young.
1801, with sunlight.
Yep, good old sunlight. He passed it through two very narrow parallel slits. Now, if light was just tiny bullets, you'd expect two bright lines on the screen behind. Simple.
But that's not what he saw.
Not at all. He saw this pattern of alternating bright and dark bands. An interference pattern.
Ah, the classic wave behavior, like ripples in a pond. Where the crests meet, it's bright. Where a crest meets a trough, they cancel out, it's dark.
Precisely. And that was, for over 100 years, considered definitive proof that light was a wave. Case closed, it seemed.
Seemed being the operative word, because the early 20th century blew that wide open.
Completely. You had things like the photoelectric effect, black body radiation phenomena that only made sense if light also acted like discrete packets of energy. Particles, what we now call photons.
So light is both a wave and a particle.
That's the emerging picture. But the real shocker came when people started doing the double-slit experiment, not just with light, but with actual bits of matter, like electrons.
Claus Johnson, 1961, he fired electrons one by one.
Well, his initial experiment wasn't quite one by one, but he demonstrated electron interference. Later experiments did go down to single particles. And guess what?
The same interference pattern.
The exact same interference pattern. And it's not just electrons. This weird duality, it's universal. They've done it with neutrons, atoms, even huge molecules made of over 800 atoms.
Wow. 800 atoms acting like a wave.
It defies intuition, doesn't it? It leads straight to this core principle, wave-particle duality. Matter and light can show wave properties or particle properties, but the crucial thing is...
You can't see both at the same time.
Exactly. How you set up your experiment determines which face it shows you.
Okay, but the single particle thing, that's where my brain starts to hurt. How can one electron interfere with itself? What does that even look like?
It's deeply unsettling to our classical minds.
Yeah.
Imagine turning the electron gun down so low, only one electron goes through the apparatus at any given time.
Right. Logically, it should go through slit A or slit B, so over time, you just build up two bands on the screen behind the slits.
That's the classical prediction, but it's utterly wrong.
So what does happen?
Each electron hits the detector screen as a single localized dot. Like a particle, exactly where you'd expect it. Ping. Then another one. Ping. At first, the dots seem random.
Just scattered points.
But as you let thousands upon thousands of these individual electron hits accumulate, that ghostly interference pattern, the bright and dark fringes, slowly builds up.
Whoa. Hold on. The interference pattern, which we just said, comes from waves interacting.
Is built up, dot by single dot, by particles that were never in the apparatus at the same time.
Yuck. That's staggering. So the inescapable conclusion is, what? Each particle somehow goes through both slits?
In some sense, yes. It behaves as if it passes through both slits simultaneously, exploring all possible paths. But when it hits the screen, it's detected at only one location. This self-interference is the absolute core of the quantum mystery. It forces us to ditch those simple pictures.
Which is where the wave function comes in, right? This mathematical tool, psi.
Exactly. To even describe this, classical physics fails. Quantum mechanics introduces the wave function. Yeah. And it's critical, really critical, to get this. It is not a physical wave, like a ripple of water or sound.
Okay, so it's not stuff. What is it?
It's a mathematical object. A complex number assigned to every point in space, actually. A probability amplitude. It contains, essentially, all the information that can be known about the quantum system before you measure it. Think of it like a wave of possibilities.
A wave of possibilities. I like that. So how does that connect to the pattern we see?
Through Max Born's rule, he figured out that if you take the magnitude of the wave function at a certain point and square it, that's x glacial 22, what you get is the probability density of finding the particle right there, at that position x in time t.
Ah, so the interference pattern isn't the particle itself spread out, it's a map of where the particle is likely to be found. Bright fringes mean high probability, dark fringes mean low probability.
Precisely. It's a statistical pattern built from many individual events, each governed by that probability distribution.
And the shape of that probability map, the interference, comes from superposition.
Yes. Before measurement, the particle isn't in slit A or in slit B. Its state is described as a combination, a superposition, of both possibilities.
Yeah.
Sun, psi, plus Sybil.
Like it's doing both at once.
In a way. And when you calculate the probability something is 2, you square that sum. This gives you terms for path A, terms for path B, and crucially, cross terms where psi and the Sybil ball interact. Those are the interference terms that create the peaks and troughs.
Okay, that's a huge shift. Classical physics gives definite answers. The ball is here. Quantum mechanics, via the wave function, gives probabilities for where you'll find it if you look.
It's a move from a deterministic description of reality to a probabilistic, almost informational one. It's fundamental.
Right. But just when you think, okay, probability, superposition, I can sort of grasp that, the experiment throws another wrench in the works. What if we try to watch which slit the particle goes through?
Ah, the act of observation. This brings us straight to Niels Bohr and his principle of complementarity.
Complementarity. What's the gist?
Bohr basically said that certain quantum properties come in pairs that are mutually exclusive. You can know one aspect precisely or the other, but never both with full precision at the same time.
Like position and momentum is the famous one?
That's the Heisenberg uncertainty principle, which is related. But for the double slit, the complementary properties are its wave-like behavior, interference, and its particle-like behavior, which path it took.
So you set up the experiment to see the interference pattern that's observing its wave nature.
Correct.
Or you set up detectors at the slits to see which path it takes that's observing its particle nature.
Also correct.
But Bohr says you cannot do both simultaneously if you get that which path information.
The interference pattern completely disappears, washes out. You just get two bands like you'd expect for classical particles.
So the very act of finding out which path it took forces it to behave like a particle and kills the wave interference.
That's exactly it. Acquiring information about one aspect destroys the phenomenon associated with the complementary aspect.
Okay, is this just magic? Does the particle know we're watching?
Yeah, it feels like that sometimes, but no. It's not consciousness or anything mystical. Observation in quantum mechanics means physical interaction.
Right. To know which slit the electron went through, you have to poke it somehow.
You got it. You need a measuring device, a detector. And that detector must interact with the particle. Maybe it scatters a photon off it or detects a tiny electric field change. Some physical process has to occur.
And that interaction is the key. What happens then, physically?
That interaction creates entanglement. The state of the particle becomes linked, correlated, with the state of the detector.
So instead of just particle A plus particle B, you get something like particle A detector A triggered plus particle B detector B triggered.
Exactly. That's a great way to put it. The which path information isn't just known. It's now physically encoded in the state of the detector. The particle and detector are now one combined quantum system.
And that entanglement with a detector, that has consequences.
Huge consequences. It leads to something called decoherence. See, your detector isn't isolated. It's a macroscopic thing. It's constantly bumping into air molecules, radiating tiny amounts of heat. It's coupled to its environment.
So information about the detector's state, whether it triggered A or B, doesn't stay put.
It leaks out incredibly fast. It gets imprinted onto countless particles in the environment, photons, air molecules, whatever. The information spreads and becomes effectively impossible to retrieve.
And this leakage, this interaction with the environment that affects the original superposition.
It scrambles it. Specifically, it destroys the delicate phase relationship between the path A part of the wave function and the path B part. Those interference terms we talked about, they rely on a precise, stable phase relationship. Decoherence washes those phases out.
And without the phase relationship.
The interference terms average to zero. The probability distribution on the screen just becomes the sum of the probabilities for path A and path B separately.
Right.
No more fringes, just the two bands, the classical result.
So the famous observer effect isn't about a mind influencing reality. It's about information and interaction.
Precisely. It's about information becoming physically encoded. A quantum system can only exhibit interference if there is absolutely no way, even in principle, to know which path it took. If any record, anywhere, is created through interaction, entanglement, and decoherence, the interference is lost.
It's a trade-off then, interference potential versus actual information.
That's a perfect way to summarize it. The weirdness is built into that fundamental trade-off.
Okay, that's the standard, albeit mind-bending quantum picture. But your source brings up this other idea, the wave dissipation hypothesis. It sounds simpler, maybe.
It definitely sounds more intuitive to our classical brains.
What's the core idea there?
The hypothesis basically says a quantum thing starts as a real physical wave. It spreads out, goes through the slits, interferes with itself like a water wave.
Okay, makes sense so far.
And then, when this physical wave hits the detector screen, it somehow dissipates, like a wave crashing on the shore, leaving behind just a point-like particle, a remnant, which is what we detect.
I can see the appeal. It feels more mechanical, less abstract than probability waves collapsing.
Yeah.
But you said earlier it runs into big problems.
It does. Big fundamental problems when you compare it to the actual quantum formalism and experimental results. First, we need to be really clear what dissipation means in physics.
Right, not just disappearing.
No. Dissipation is a specific thermodynamic process. It's about organized energy turning into disorganized energy, usually heat, because of interactions with a medium. Think friction, viscosity. It implies an irreversible loss of energy or amplitude from the wave itself.
Okay, so how does this wave dissipation idea stack up against actual quantum mechanics?
It falls apart pretty quickly. It's what philosophers might call a category error, trying to apply concepts from one domain, classical waves, thermodynamics, where they just don't fit quantum phenomena.
Point one.
Point one, and this is the absolute killer. The wave function is not a physical wave made of stuff or energy.
We established that. It's a probability amplitude. Mathematical, informational.
Exactly. You can't dissipate a probability amplitude like you dissipate the energy in a water wave. How would you even turn a probability into heat? It doesn't make physical sense. It confuses the map with the territory, the particle's potential behavior.
Okay, so the central object of the theory isn't the kind of thing that can dissipate. What else?
Conservation laws. First, conservation of probability. Quantum mechanics insists that the total probability of finding the particle somewhere must always be 1. It's called normalization.
The particle has to be somewhere.
Right. What we call measurement or collapse doesn't destroy the particle or lose probability. It relocalizes the probability. The wave function instantaneously changes, so all the probability becomes concentrated to the point of detection. It's a sudden shift, not a gradual fading away or loss. Dissipation implies loss. Collapse implies relocalization. Very different.
So the math is different. The concept is different.
Completely. And third, the hypothesis gets the detected point backwards. It talks about the particle being a remnant of the dissipated wave.
Implying the wave is primary, the particle secondary.
Yes. But in standard quantum mechanics, the particle, electron, photon, is the fundamental entity. The wave function describes its state, its potential. Detection is the particle interacting and revealing its localized particle-like aspect. The particle doesn't emerge from a dying wave. The wave-like behavior is just how that fundamental particle's probability distribution behaves before interaction.
It flips the script on what's fundamental.
It does. And finally, there's energy and momentum. Any real physical process, like a measurement interaction, has to conserve energy and momentum.
Standard physics 101.
Right. Quantum mechanics handles this perfectly. The interaction between the particle and the detector involves exchanges of energy and momentum that are all accounted for. The wave dissipation idea, it's completely silent on this. How does this supposed dissipation conserve energy and momentum? It offers no mechanism.
So summing it up, the wave dissipation idea fails because it treats the wave function as a physical substance. It violates probability conservation, it misunderstands the particle-wave relationship, and it ignores energy-momentum conservation.
That's a perfect summary. It's an intuitive classical analogy wrongly applied to a quantum reality that runs on fundamentally different probabilistic and informational rules. Interaction, entanglement, decoherence, probability relocalization. That's the accepted, mathematically consistent picture, even if it bends our minds.
Okay, so we've dismantled the nice, simple, intuitive dissipation idea, which means we're forced back to confront the weirdness of the standard picture, specifically that collapse.
And that is where we hit the wall, the measurement problem. Arguably the biggest unsolved mystery in fundamental physics.
Why is it such a problem? We have the math. It works.
Because quantum theory seems to give us two completely different contradictory rules for how things evolve over time.
Rule 1.
Unitary evolution, governed by the Schrödinger equation. As long as the system is not being measured, its wave function evolves smoothly, continuously, deterministically. Superpositions are preserved. The particle stays in that both slits at once state.
Okay, smooth sailing when unobserved. Rule 2.
Wave function collapse. The measurement postulate. The moment a measurement occurs, the wave function stops evolving smoothly. It changes instantly, discontinuously, and probabilistically. It jumps from that superposition of many possibilities to just one definite outcome, the one you actually measured. The electron suddenly is at that specific point on the screen.
And the contradiction is?
Quantum theory gives us no clear objective rule for when to switch from Rule 1, smooth evolution, to Rule 2, sudden collapse. What counts as a measurement? Does it need a conscious observer, a Geiger counter, a single atom interacting? Where do you draw the line?
This sounds like that shifty split or Heisenberg cut you mentioned, this arbitrary line between the quantum system and the classical measuring device.
Exactly. Where is that boundary? What makes an apparatus classical enough to trigger collapse? Is a large molecule classical? A virus? A cat?
Ah, the cat. This leads inevitably to Schrödinger's cat, doesn't it? His thought experiment from 1935.
The ultimate illustration of the problem. You've got the box, the radioactive atom, quantum system, the Geiger counter, hammer, poison vial, measuring apparatus, and the poor cat.
The atom's decay is probabilistic, let's say 50-50 chance in 1 hour.
Right. So according to Rule 1, Schrödinger equation, after an hour, if no one's looked, the atom is in a superposition, decayed plus undecayed.
Still following?
But the counter, hammer, poison, and cat are all linked to the atom. They're part of the system.
Right.
And the Schrödinger equation is linear. If it applies to the atom, it should apply to the whole chain.
Oh boy. So if the atom is decayed plus undecayed, then the cat
Must also be in a superposition. Dead cats plus alive cats, simultaneously. Until someone opens the box and performs a measurement.
Which is just absurd. We never see cats that are both dead and alive. We open the box, the cat is definitively one or the other.
Precisely. That's the measurement problem laid bare. If quantum mechanics is the fundamental theory of everything, including cats and detectors, it shouldn't predict macroscopic absurdities. The standard formulation seems incomplete because it doesn't explain how or why the superposition resolves into a single reality upon measurement, or even what constitutes that measurement.
Okay. Deep problem. No easy answers.
So how are physicists trying to solve this? You mentioned a cacophony of solutions.
Interpretations, right?
Interpretations, or in some cases, actual modifications to the theory. And yeah, after almost a century, there's still no consensus. Each approach comes with its own philosophical baggage, its own price of admission.
Let's survey the main contenders. What's the traditional view? Copenhagen.
Copenhagen interpretation. Less a single coherent doctrine, more a collection of views from Bohr, Heisenberg, Born in the early days. It was the default for a long time.
It's a shut up and calculate approach.
It kind of became associated with that, yeah.
Right.
Pragmatic. It emphasizes intrinsic indeterminism. Randomness is fundamental. Probabilities are given by the Born rule. Complementarity is key.
And the wave function itself, is it real?
In Copenhagen, it's generally considered epistemic. It represents our knowledge or information about the system, not the system's objective reality.
So collapse isn't a physical process.
It's an update of knowledge. When a measurement provides new information, our description, the wave function, changes. Asking about the cat before opening the box is deemed meaningless because the property, alive dead, didn't have a definite value until measured.
Deterministic or random.
Fundamentally indeterministic. Randomness is real.
Relativisms.
Imprecise. Doesn't clearly define measurement or the cut. Philosophically unsatisfying for many who want an objective description of reality.
Okay, what's an alternative? You mentioned modifying the equation.
Right, objective collapse theories. GRW, Girardi-Rimini-Weber, or CSL, continuous spontaneous localization, are examples.
What do they propose?
They say the Schrödinger equation isn't quite right. They add new, tiny, nonlinear, random terms to it. These terms cause wave function collapse to be a real objective physical process. It happens spontaneously all the time, everywhere.
Independent of observers.
Totally independent. The wave function here is onvrotic. It's real stuff, or describes real stuff.
So collapse is a physical event. How does that solve the cat problem?
The collapse probability depends on the number of particles. For a single atom, spontaneous collapse is incredibly rare. But for a macroscopic object like a cat, or even a dust mote, or the Geiger counter, with trillions upon trillions of particles, the cumulative probability means it collapses almost instantaneously. Macroscopic superpositions just can't survive.
Deterministic.
Still indeterministic because the collapse events themselves are random.
Criticisms.
It requires adding new physics, new universal constants, whose values are basically chosen to make the theory work. And while it's testable in principle, these collapses should produce tiny amounts of heat experiments. Haven't found any evidence yet.
Interesting. So Copenhagen says collapse isn't real. Objective collapse says it is real and modifies math. Any other options?
Oh, yes. The no-collapse interpretations. They say the Schrödinger equation is always right, and collapse never actually happens.
How can that work? We see definite outcomes.
Two main ways. First, the de Broglie-Bohm pilot wave theory, or Bohmian mechanics.
Pilot wave.
Yeah. It says particles are always particles, with definite positions, even when unobserved. These are the hidden variables. But there's also a real physical wave, the wave function, the pilot wave, that guides the particle's motion.
So the wave function is real and the particle's position is real, ontic, all around.
Both ontic, yes. In the double slit, the particle really goes through only one slit. But the pilot wave goes through both, interferes with itself, and then steers the particle towards the high probability regions, bright fringes.
So what's collapse in this picture?
It's only apparent. When we measure, we discover the particle's pre-existing position and our knowledge of the pilot wave updates, but nothing physically collapses.
Deterministic.
Fully deterministic. Given the initial position in pilot wave, the future is fixed. Probabilities only arise because we don't know the particle's exact starting position.
Criticism.
It has to posit these hidden variables, the exact positions, and it's inherently non-local. The pilot wave connects everything instantly, which Einstein famously disliked spooky action at a distance. Many find that deeply counterintuitive, too.
Okay, one more no-collapse theory. The big one.
The many worlds interpretation, MWI, from Hugh Everett III.
This is the parallel universes one, right?
That's the popular takeaway. MWI takes the Schrödinger equation completely literally. It says it applies universally, always. Collapse never happens.
The cat. Measurement.
At any interaction that looks like a measurement, the entire universe branches. The superposition doesn't resolve. Instead, all possible outcomes happen, each in its own separate parallel world or branch.
So in one universe branch, the atom decayed, the cat is dead. In another branch, the atom didn't decay, the cat is alive.
Exactly. The wave function here is on-physic. It describes the entire multiverse. And its evolution, according to Schrödinger, is fully deterministic.
Cool.
Non-existent, just branching.
Determinism.
The overall multiverse evolution is deterministic. But from the perspective of an observer within a branch, things appear probabilistic according to the Born rule, though deriving the Born rule cleanly in MWI is still debated.
Criticisms.
The main one is ontological extravagance. Do we really need to believe in an infinite, ever-splitting number of unobservable universes just to avoid collapse? It makes no unique testable predictions compared to standard quantum mechanics.
Wow. Okay, that's a lot of options. None of them simple. What about decoherence? Where does that fit back in?
Good question. Decoherence is crucial, and it's part of the story in almost all interpretations, but it doesn't solve the measurement problem on its own.
What does it explain then?
It explains why the world looks classical to us. It explains why we don't see macroscopic superpositions like the alive-dead cat. Any such superposition would entangle with the environment so fast decohere that the interference between the alive and dead possibilities vanishes almost instantly. It turns the quantum A&D into a classical OR.
Okay, so it explains the disappearance of interference between macroscopic possibilities.
Yes, but what it doesn't explain is why, when you look at the cat, you experience only one specific outcome, either alive or dead. Decoherence gives you a collection of effectively separate branches or possibilities, but it doesn't single one out for your experience. This is sometimes called the problem of outcomes.
So it gets rid of the weird quantum interference between cat states, but not the problem of why I only see one state.
Exactly. You still need an interpretation about Copenhagen's knowledge update, objective collapse's real event, Bohm's particle path, or many worlds branching to deal with that final step. Decoherence is a vital piece of the puzzle, but not the whole solution.
Okay, let's try to quickly recap the interpretations then. Copenhagen.
Epistemic wave function, knowledge update, indeterministic vague cut,
Objective collapse.
sonic wave function, real physical collapse, indeterministic, modifies quantum mechanics,
De Broglie-Bohm.
ionic particle plus pilot wave apparent collapse, deterministic, non-local, hidden variables.
And many worlds.
Ionic wave function, multiverse, no collapse, deterministic multiverse, ontologically extravagant.
So pulling this all together for you, the listener, that intuitive wave dissipation idea, it's a non-starter. It fundamentally misunderstands what the wave function is and clashes with basic quantum principles.
Right, it's a category error. The real process involves interaction, entanglement, decoherence, and this mysterious probability relocalization we call collapse or something even stranger, depending on your interpretation.
And by refuting that simple, classical-sounding explanation, we're left staring into the abyss of the measurement problem. The fact that we have all these radically different interpretations, none fully satisfactory or proven, tells you just how deep this puzzle runs.
It really does. The double-slit experiment, in all its variations, remains this incredibly powerful, almost humbling lesson from nature.
It forces us to accept that reality at its deepest level just doesn't play by the rules of our everyday intuition. We have to let go of simple mechanical pictures.
And embrace a more abstract, mathematical, and frankly stranger description of the world.
So the final thought for you. A century on, this experiment is still our clearest window into the quantum realm. It challenges you constantly. It makes you ask fundamental questions about observation, about information, about what it even means for something to be. What is the nature of reality when the act of looking seems to change what's there?
That's the mystery Feynman was talking about, and it's one we're still wrestling with today.